Hey there, stats enthusiasts. Welcome back to our AP Statistics series on Unit 7, Inference for Quantitative Data Means. I'm Goldie, and I'm going to be taking you through Notes 4 today, which is for a confidence interval for a difference in means. We're going to be going through our sampling distribution for a difference in means again, and then we are going to be talking about how we apply our confidence interval knowledge to this difference in means. So it's going to be a great lesson today, so go ahead and sit back, relax, and let's dive into the content. It has been a while since we have discussed sampling distribution of a difference in means. So let's go over what the sampling distribution looks like. We are going over this because for our confidence intervals for a difference in means, it is going to be constructed with the sampling distribution. So what we see for shape, center, and spread, as well as conditions, is going to translate over into our confidence intervals. So the shape of the sampling distribution when you combine is going to be approximately normal. As long as either both sample sizes are greater than 30, we can claim the CLT. If one or both samples are less than 30, each population should be normal or approximately normal here. Now, this was true for our sampling distribution. What we're going to see with inference here in a little bit is that we sometimes don't know information about our population. And when that's the case, we might have to graph our sample data to make an assumption about our population. So we're going to get there. The center of our sampling distribution, remember if we have two centers, then when we combine them for a difference, the center is just the difference of those two population parameters. And we could do this as long as both samples were randomly selected, or in an experiment, both samples were randomly assigned. Both treatments were randomly assigned. And then lastly is spread. So spread, I'm going to take you through just the quick proof of what the sampling distribution standard deviation looks like again. If we have two individual distributions, these are going to be each of their sampling standard deviations. And then we know that when we combine by subtracting, we always add variances. So we're going to take the variance, and the variance of each of these, we square each of these to get the variance. We add those variances together, and then to get the standard deviation, we take the square root. So that's what we're looking at on the screen right now, is we have the square root of the sum of those variances, because we always add variances. And then if we clean up a little bit here, like numerator gets squared, denominator, when that gets squared, the square root goes away. So then we have the standard deviation of the difference. This is why it looks like the square root of the sum here. Okay. And then this was true as long as the 10% condition was satisfied for both samples. And again, that was only when we were sampling. If it was an experiment, we didn't need to check that part. Okay. So a little bit more about this. Okay, because obviously they use the population standard deviation, which we know is not always going to be known. And because of that, we have to use our sample standard deviations instead. We're going to use both sample standard deviations, one from the first group and one from the second group. And as always, it introduces some error, and that's why we call it the standard error, as an estimated standard deviation of our sampling distribution. So we're going to switch over to S to represent, sample standard deviation here. But the formula is the exact same. We're just going to use S instead. Okay. Otherwise, all the components of our confidence interval we know. We know the difference is going to be our statistic plus or minus our critical value times our standard error, which we just talked about. Our critical value is going to be found the same way as always. We are going to use our T star for means because we are using our sample standard deviation here. The one thing that is new is that what happens when we have two sample sizes and we need to find degrees of freedom. How do we find degrees of freedom when we have two sample sizes? Well, there's actually two ways we find degrees of freedom. The first way, option one, is this exciting formula. Okay, I mean, look at it. It's beautiful. You know all of those components, but putting it together is quite the mess. Okay, and it never gives degrees of freedom as a whole number. Okay, so this is option 1. It's basically combining our sample sizes as well as our standard deviations here. Now, I show you this. You do not have to know this formula at all. It's nowhere on your formula sheet and you will never have to use it. But this is how your calculator and any technology you use, this is how they find degrees of freedom. And when it reports degrees of freedom to you on your calculator, you are going to get a decimal. Okay. And if you're like, where is that decimal degrees of freedom coming from? It is coming from this formula. Okay. So we will not use it. We will not use this formula, but you can report that decimal degrees of freedom from your calculator. And option 2, this is going to be a by hand option, is when you take the smaller of degrees of freedom. So you find degrees of freedom for your first sample size and your degrees of freedom for your second sample size, and whichever one is smaller, that is the one you go with. This is considered a conservative method because the confidence intervals that you get will have a margin of error as large or larger than needed. And when we get into a significance test, using this option 4 degrees of freedom will give a p-value equal to or greater than the true p-value, meaning that it basically errs on the side of caution, and it makes sure that we don't make a margin of error too small, and it makes sure we don't give a p-value that is too small. Okay. So you can use either option when you actually go to run your inference procedures. I say you can use either option because if you use your calculator, you can write down the degrees of freedom that your calculator gives you. And that is a totally valid way of doing the 4-step process for inference. Or you can write down this way, option 2, what the smaller one is, when doing it by hand. Okay. I'm going to do option 2 for today, because I'm going to talk about how to use your calculator in our last set of notes in this unit. And then I'll comment a little bit more about it there. So option 2 is what we're going to go with today. So conditions. Again, the same guidelines for our sampling distribution. 2 random samples or randomly assigned to 2 groups are independent. You check if you're sampling, don't check if you're running an experiment. And then for our normal/large sample, or our nearly normal condition, either both populations must be normally distributed, both sample sizes are larger than 30, or if we have smaller than 30 sample sizes, we graph to check for no outliers or strong skewness. Which brings us to our 2 sample t-interval for a difference between 2 means. And it's quite the mouthful, but the confidence interval is created with the template you already know. When those conditions are met, the C% confidence interval for that difference is going to look like this. It is our statistic plus or minus our critical value times our standard error. So all of those components we know are brought together for this 2 sample t-interval for a difference. Okay. So T star still represents that critical value with C% of its area between negative T star and positive T star. And the degrees of freedom, you can do one of 2 ways. Either of these are accepted on the AP exam. And this is why it's very important to write down the degrees of freedom that you are using in the problem, is because when someone is reading your work, they need to be able to see what degrees of freedom you used in order to calculate your p-value. So you can use the smaller of n-1 minus, or n's, dang it. You can use the smaller value of n sub 1 minus 1 and n sub 2 minus 1. Or you can use technology to report that combined degrees of freedom. And you're not going to use the formula to do that. Please don't use that formula. You would only report this combined degrees of freedom that your calculator would give. Okay. Let's get into an example. Okay. So studies have suggested that drinking at least 4 cups of coffee a day reduces strokes. And this is believed to be because coffee has these things called polyphenols that promote healthy blood vessels and dampen that inflammation that can lead to strokes. So in an experiment, 20 healthy women were assigned randomly to drink 3 cups of coffee a day or drink no coffee for 2 weeks. And the level of polyphenols in their blood was measured before and after. And here are the percent changes before minus after of the polyphenol levels. Okay. Now we just, in the set of notes before this, we talked about matched pair procedures. And I want to talk about why this would not be a matched pair procedure. Okay, so looking at the data, your first thing you notice, you have coffee and no coffee. Okay, and then you have to think, how were these values obtained? Was this obtained on the same subject? Okay, because if it was obtained on the same subject, then it would be a matched pair procedure. But in this case, it was not. Okay, they said they took 20 women and assigned them at random to either drink 3 cups of regular coffee or drink no coffee for 2 weeks. So each woman was randomly assigned to one treatment. Okay. Another thing that really messes with students is that they measured percent changes. And so you think, oh, I'm measuring a difference, so I have to run a matched pair procedure. And that's not the case here either. This is just the quantitative value, the quantitative variable that was measured. Okay. So because it's what we're measuring, this just represents the percent difference, right? That's just what we're measuring. And we're looking at those level of polyphenols in their blood, okay? So our question is, why will we be creating a 2 sample t interval and not finding the difference using a 1 sample t interval on the difference, which would be a matched pair procedure? So you have to be able to explain what I just told you, right? Is because the pairing of coffee versus no coffee is not a matched pair design. It took 20 women, randomly assigned them to 3 cups or no cups. Okay? And then we compared them after, right? The before minus after, and then we're going to compare the difference, okay? That was just a completely randomized design. It was not a matched pair design. So you have to be able to determine those design differences, okay? B, construct and interpret a 90% confidence interval for the difference in mean percent changes in those polyphenol levels, okay? So first, we want to define our parameters, right? Where mu sub 1 is the mean percent change for coffee drinkers, and mu sub 2 represents the levels for non-coffee drinkers. I like using 1 and 2, but you can easily, make the subscript C and N, C for coffee drinkers, N for non-coffee drinkers. It's going to be whatever you would like, okay? And then because this is going to be a 90% confidence interval, we want to find our T star value. Okay, so T star, what I'm going to use degrees of freedom as 9 because I have 10 coffee drinkers and 10 no coffee drinkers. The degrees of freedom for each of those groups is going to be 9. So I'm just going to use degrees of freedom of 9. My inverse T with my area of 0.05 degrees of freedom of 9, that's going to give me my T star value that I'm going to use. Okay. I also need to find my summary statistics. Now, I chose to write them down right now, but you can easily write them down a little bit later in your calculate part of your inference steps. I wrote them down now. I put all of the data into L1 and L2, and I ran 1-bar stats on each of those lists. Okay, I got my N, I got my X, and I got my S. Now I want to check my conditions. The subjects were randomly assigned to treatments, so I'm all set there. Don't check independence because I did not randomly sample from the population. And I need to make sure that I show histograms of each group and that there's no outliers or strong skewness. So again, because I had my data in L1 and I had my data in L2, I went ahead and I could make my graph on the calculator, okay? I made sure I had even intervals here for that difference between coffee and no coffee. Now, they don't start at the same spot. That is okay because you're doing two separate distributions, and all you're checking for is no outliers or strong skewness. Now the calculate piece. I'm going to run a 2-sample t interval for a mean, and I'm going to write down my skeleton formula here. On the AP exam, remember you only have to do one of these. Okay? I'm doing both of them just to show you both, but you either have to name the test with words or name the test with the formula, and that is very important that you do. Okay. I can take all my values now and substitute them into my formula. Okay. And here's where you could turn to your calculator to give you that confidence interval. Again, I'm going to show you how to use your calculator in the last set of notes for this unit. Right now, I'm going to do it by hand. Okay. And by hand, I get 4.74 plus or minus 2.151. All right. And I could also report that as interval notation, which is a little bit more common. It's what the calculator gives. Okay. And then I conclude with my confidence interval. We are 90% confident that the true mean difference in polyphenol levels, coffee minus no coffee, is between 2.589 and 6.891. Okay. So because this interval is positive, right? We have positive values for our true mean difference. That implies that the polyphenols are going to be higher, are raised more in coffee drinkers. Okay. And that kind of leads into our part C. Okay. Does the interval suggest that coffee is more effective at producing polyphenols? Okay. Because our interval is positive, our confidence interval does not contain 0. And because the difference was coffee minus no coffee, that implies that coffee had higher levels of polyphenols. Okay. So because of the confidence interval does not include 0, it does suggest that coffee is more effective at producing those polyphenols. Okay. This is going to lead into our next set of notes where we run a significance test for 2 samples. Okay. And remember the relationship between confidence intervals and significance tests. It is an important one. And that's what part C is kind of leading you to remember, is that we can make conclusions about some claims based on a confidence interval that we see. And that wraps up today's lesson on confidence intervals for a difference in means. Our next video is going to be Notes 5, where we run a significance test for a difference in means. So if you're ready, go ahead and jump ahead to that video. If you have liked this video, please click the like button and subscribe to my YouTube channel for more great AP statistics content. I wish you endless statistical success, and I will see you in the next video.